Okay, so a brief review of 6.1 that I want you to do. And this is about the atom and its nucleus. And so let's start off with that Geiger-Martin experiment. Geiger and Martin, and they were under Rutherford's direction. Remember, they were graduate students basically for him. And if you recall, they did the gold foil. So think about that gold foil. Actually, there's a quote from Rutherford that was quite interesting. When he first discovered, he said that this experiment was like shooting a cannon at a piece of tissue paper and having the cannonball bounce back. So pretty cool to think about that. So the gold foil, very, very, very thin gold foil. You watched that little video on that guy from Chicago that showed how he made gold foil, and they were shooting alpha particles at it, which is a pretty massive particle. It's the nucleus of a helium atom, and a lot of them went straight through, but some were not. And the reason that they were not is because Thomson's plum pudding model didn't really hold up right. And so here, this being the nucleus, so nucleus, as you know, has protons and neutrons, so it's positively charged in nature. And then here comes the nucleus of a helium atom, and of course it's positively charged in nature. And so as it approaches it, it starts encountering the field of the nucleus, and it gets deflected. And so that leads to the idea of closest approach. And so in order to get, let's continue on with that thought, the Geiger-Martin experiment under the guide of Rutherford. Anyway, this led Rutherford to come up with his model, that sort of simple planetary model, if you will. The orbit, the electrons are in orbit. And I want to draw that right down here. So here's the nucleus, and then the electrons are in orbit around it. This led to some issues later on as to how that electron could stay in there, but we'll talk about that later. So there's the electrons. Let's just make a simple hydrogen atom. So that would be the electron's velocity, and then that would be the force, electromagnetic, K Q1 Q2 over R squared. This would be the force on the electron. So this again, as I said, was the nucleus. So here we go. Because these particles were being scattered, these helium nuclei were being scattered, and so maybe one up here would go like this, and then one going directly at it actually might just come back on itself. And this led Rutherford to come up with that there must be a dense central core, and then he thought that the electrons were orbiting around the outside, the very much less massive electrons. So keeping going, let's got to go faster than that. So the consequences were that it got rid of the J.J. Thomson's idea of the plum pudding model. And then in order to get a better understanding, real quick, you had the idea of closest approach. And we'll revisit this, ACH. So here's a nucleus. If you could get enough energy, you could get very, very close to it. And from the scattering pattern, you could come up with, that one even touched, you could come up with the approximate size of it, of the atom. And if you recall, they came up with a nice equation where the radius of I said atom, I meant nucleus. The radius of a nucleus of an atom is equal to 1.2 times 10 to the I'm sorry, not times 10, my fault. It's not 1.2 times a to the 1/3 times 10 to the minus 15th meters, and that a is the number of neutrons and atomic mass 1, so you can't do that. They're neutrons and protons. Okay, so your opening problem has one like that, and I'm going to try to approach that and give you a little bit of setup for that. So there's another model of the atom, which ended up being the Bohr model of the atom, which came from basically emission spectra. So emission, which we visit a lot in the upcoming chapters, and we'll see it quite well. But and I've shown you enough on this with the PhET simulations. But in this one, you had n equal 1 n equal 2, n equal 3, and n equal 4, for instance, and whereas n equal 1 is the ground state. And then if an electron goes up a level, so to here, so let's say it bounced up, went up to here in a straight line maybe, it doesn't matter, and then as it came back down, it would emit a little photon of light and frequency of light. And we're going to find out, I'll give you this equation right now, that let me just get rid of that. E equals h times f. And so the energy of a photon is equal to Planck's constant h times its frequency. And so so Bohr came up with his energy level concept, the Bohr model. So this is the Bohr model. And then the other one was the Rutherford model of the atom. So let's see. Just to wrap up 6.1, we also talked about how that if you had an element, let's just say X, element X, and you wanted to know the number of protons in the nucleus, that would be Z, and I think it was A, if I'm not mistaken, was the number of neutrons and protons. So therefore, A minus Z equals the number of neutrons. Let's make that an N. And this was the protons and neutrons. Remember, collectively, a proton or a neutron is called a nucleon. And this is the number of protons, or the atomic number. All right, so pretty simple. And then we got to just the 4 fundamental forces, so going strongest this way. So we had gravity, and then the weak nuclear, and then electromagnetic, and then strong nuclear, and in that order. So strongest going upward. So therefore gravity is the weakest, then weak nuclear, then electromagnetic, and then finally strong nuclear force. And that was basically it for the 6.1, the big parts of what I wanted to get across to you, that the spectrum, the emission spectrum that led to Bohr's model of the atom. And we'll look at that more deeply, but just know that the emission spectrum led to Bohr's model, the Rutherford model of the atom that sort of got rid of the the J.J. Thomson idea, the idea of closest approach. And let's see, the other thing that we want to bring up, I know, I think there's one more term, I was just looking at your objectives, the nuclide. And that was a specific number of protons and neutrons. So a nuclide has a specific number of protons and neutrons. It's horrible spelling. N-E-U-T. And so what this means is, for instance, hydrogen. So 1 and 1, so it has 0 neutrons, so that you could call that a nuclide. Or helium, the common helium, so 4 and 2. So you know that when it's this helium, it has 4 and 2, it's not an isotope of it. So a nuclide is just a specific number of protons and neutrons. Okay? All right, that's it for this one.